Yes. So we'll have 3 talks in this session. The idea is to have 30 minutes for the talks themselves, followed by 10 minutes of questions. And for the speakers, I will give a warning 5 minutes before the end of the 30. So without further ado, I'm happy to pass the floor to Licia Verde, who will update us on Hubble troubles.
Thank you. Let me do this magic trick of sharing the screen and see how that goes. Okay. Do you see my slides?
Yes.
The real one. Okay, good. Okay. So thank you for inviting me to talk about this very exciting and very interesting meeting covering very timely subjects. And I've been asked to talk about the Hubble tension, which I call the Hubble troubles. And I was thinking it's really fitting here because the title of the conference reminds us that there are deep connection between cosmology and the standard model of cosmology to fundamental physics and the standard model, for example, of particle physics. And both fields for a while have been looking for physics beyond the standard. For cosmology, this is relatively recent, given the fact that we didn't have a standard model until, say, 20 years or so ago. And then we concentrated on shrinking the error bars around the parameters of this standard model for a while. But in looking for possible physics beyond the standard, how would that play out in cosmology, which is a field where we only do observation and we don't do experiment? It may play out maybe in a different way than it would play in other branches of physics. And I like the Hubble tension because it's an example of how a signature for something non-standard may actually show up. I'm not saying that this is it. I'm saying that this is a wonderful example of how something like this may show up in cosmology. That is, probably you get a tension that at the beginning is 3 sigma and nobody pays attention, of course, because 3 sigma, it's not statistically significant. And then the data gets a little bit better and it becomes 3.5, then it becomes 4, then it becomes 4.5, and then suddenly everybody wakes up and say, oh, what's going on? Maybe we should look at this. So this is exactly what's going on here. The history is of a constant non-constant, and this is a snapshot of the very recent history. So until the cosmic microwave background data had a lot of statistical power on the very large scales, there was no apparent tension between local measurement of the expansion rate of the universe that are done with a cosmic distance ladder, so based on, as Hubble was doing, Cepheids and then pushing into supernovae, and some very model-dependent determination, which is obtained by fitting parameters to a model, because the cosmic microwave background does not measure the current day expansion of the universe. It constrains the parameter of a model, and one of these parameters is being interpreted as the current day expansion rate of the universe. But with the Planck, when a lot of statistical power went to smaller L, then we started seeing this difference. And in the last couple of years, this new measurement of the tip of the red giant branch came in, which lies in the middle of the two, and I'll say something more about it. So the measurement, the local measurement that has the smallest error bar to date is the measurement from the SHOES collaboration, which is the standard cosmic distance ladder. As I was saying, it's parallaxes to Cepheids, and then Cepheids into supernova, and then the supernova into the Hubble flow, to measure what is said in the CAN, which is distance versus recession velocity, which is straight the Hubble law. And so this is this green constraint here. This is cosmological model independent. The other very tight constraint that we see here in red, it's from the Planck 2018 data release. But this is a model dependent determination and lies in the range of 67 to 68. In the meantime, after that, other two measurements came in of relevance. One is the constraint from baryon acoustic oscillation, adding some assumption about early time physics, but not data about early time physics, which is BAO plus BBN. This is also a model-dependent determination. And then this tip of the red giant branch, which lands in the middle, that started gaining attention in 2019. So let me say a few words about this. The model-dependent measurement are these two. The model-independent or cosmological model-independent measurements are these. So what is the tip of the red giant branch? The tip of the red giant branch is a way of actually doing a cosmic distance ladder with standard candles, but the standard candles now are not Cepheids, are in the HR diagram of galaxies and cluster that you see next to our Milky Ways. There is a point where we know there is degenerate helium core mass luminosity relation, and that tip, basically, if you can know very well the extinction, then gives you a standard candle, and then you can do a cosmic distance ladder bypassing the Cepheids and going directly into tying this into supernovae. And so this is what they've done in this work, and the calibrators between tip of red giant branch and supernovae in order to be in the Hubble flow, there are 18. So the 18 object, and then this relation goes into the Hubble flow. The other traditional method has one extra step. I shamelessly stole this slide from Adam Rees' talk of its determination with the Schu's collaboration of the Hubble constant. Then there are geometrical measurement to parallax of the Cepheids, and then the Cepheids that calibrated on the supernova, and there are 19 of those, and the trick is to get more of those to link these two and then go into the supernova that gets into the Hubble flow to measure the Hubble constant. And this local measurement is the one that hangs around 74. So the other things that I mentioned are the baryon acoustic oscillation. And I'm sure that I don't have to explain to the majority of this audience what the baryon acoustic oscillations are, but let's run through it to know how they can be used. So the physics is that sound waves in the early universe propagate until radiation and matter decouple. In reality, it's a radiation drag, but let's not be too peculiar about this. This imprints a scale, which is a standard ruler, which corresponds to a sound rise on a radiation drag. And this is a key observable. It is useful to measure the geometry of the universe, dark energy equation of state, or even modification of GR that show up in the expansion history. And it's the early universe physics that is well known that sets it. In other words, what we are seeing is basically the same oscillation that we've seen in the acoustic peaks of the cosmic microwave background, and they were so useful to define the standard model of cosmology. But instead of seeing them in photons, which is what we see in the CMB, we see them in galaxies that are tracing the dark matter distribution that has been coupled to the baryons through gravity. So CMB observation and early universe physics in a lambda CDM universe constrain the standard ruler length to 0.2%. This is precision. The nice thing that the community has been able to start doing since 2010 or so is to tie in together standard ruler and standard candles. So supernova has been known for a while to be standardizable candles. They gave us the accelerating universe, and they gave us lambda. They are really good at measuring relative distances because there is a large uncertainty on their absolute magnitude of a fiducial supernova, but for relative measurements, they are great. Baryon acoustic oscillation, on the other hand, are able to measure absolute distances To get the same precision as the supernova, we had to wait until, well beyond 2010, because you need large volume. This is a statistical measurement of something that is of the order of 150 megaparsecs. So you need to be able to survey large volume of the universe, and that required a lot of effort. But depends on the value of the sound horizon radiation drag. So it really requires assumption about the early time physics, although the early universe is simple, it's linear, and it's a part of the physics of the model that we really like and love and we're confident with. And the supernova and the BAO end up meeting and overlapping in redshift, so that now they can be calibrated to one another. So this made possible around 2015 or 2016 to build two ladders, what I call the direct cosmic distance ladder and the inverse cosmic distance ladder. So the traditional cosmic distance ladder was just calibrating, measuring H0 and tie that into the supernovae. But now, since the supernovae can be calibrated on the baryon acoustic oscillation, and the baryon acoustic oscillation are then automatically calibrated because of the physics in the early time physics, then we've been able to extend this direct cosmic distance ladder from now all the way to recombination. But by the same token, one can build an inverse cosmic distance ladder. So the early time physics give you the standard ruler. The standard ruler is seen in the BAO, then this BAO are tied into the supernova, which calibrate the standard candle, and that get you back to redshift 0 and to H0. So what's happening here is that in a lambda CDM model or simple variation, these two ladders do not match. And there's no much wiggle room in the middle to stretch or twist or tinker with this ladder. It's just that the two anchor points don't agree with each other. So the H0 problem can be seen as an RS problem or sound horizon radiation drag problem, and vice versa. So in this plot, the error bars are still large because this plot is from 2016, where it was showing the sound horizon radiation drag determination from the cosmic microwave background, the local measurement of H0, and how baryon acoustic oscillation plus supernova could actually tie the two in this transversal relation. More recently, this has been done with much improved data, and qualitatively the same thing happened, but of course the error bar have improved. So H0, I see it like an end-to-end problem, because you have something that you measure here and now, and it's really the expansion history of the universe, and that same quantity within your model, it's inferred by observation of the baby universe, and you have something in between that links the two. But given the size of the error bars, 0.2% on the sound horizon radiation drag from the CMB, and 1-point-something% in the shoes determination of the Hubble constant, then it's really like threading a needle from the other side of the universe. And threading needle is notoriously difficult and frustrating. You usually don't get it at the first time. So this is what's going on here. And indeed, good ladders need two good anchor points. This one doesn't, and the cosmic distance ladder, the direct and invert cosmic distance ladder, looks like they are a little bit wobbly in the anchor points. So is there a problem? I would say yes. Even George Statue, who has been for a while a strong proposer of the fact that there was no problem with H0, would now, I think, agree that there is a problem. Of course, how much of a problem is cosmological model dependent. We can quantify it in a lambda CDM. If we go away from a lambda CDM, then the problem becomes, the statistical significance becomes a little bit different. More importantly to me is, where is the problem? Now, of course, you can always invoke systematics. We all have skeleton in the closet. Every experiment are skeleton in the closet. Systematics are always there, ready to get you. As the statistical precision hits the percent, then systematics are really a big problem. For this reason, there has been a huge effort from the entire community to actually reanalyze and re-obtain the results published by the original collaboration. And as you know, it's becoming more and more common to actually put everything public, the data, the software, the intermediate step. So anybody can, try to repeat and see and do internal checks and so on and so forth. It's not a glamorous job to do, but it's important and people are doing that. So this is becoming increasingly unlikely. I mean, dumb systematic error are probably not the source. Probably if it is a systematic, it's a sophisticated one because too many eyes have looked at it in many different ways. So one possible working hypothesis is to say, well, maybe we have an early versus late problem because there's no much wiggle room in the middle of this cosmic distance ladder. Is the two anchors that don't match. So let's keep working with this working hypothesis and ask, is the problem in any specific data set if we keep some standard lambda CDM context? So if you want to put the blame into early observation, then you say, well, but H naught early doesn't budge if you take away Planck, or now even CMB data completely out of the question. So before 2019, people could drop the Planck data, but then they had to use instead the WMAP plus AC and SPT. And things didn't change, which means that is not a particular systematic having to do with Planck experiment or Planck data. But since 2019, and this paper here in particular, Schonenberg et al., they threw the CMB data completely out of the window for this analysis. And even for simple extension to the lambda CDM model, where you have an extra number of effective neutrino species, the tension is still there. So they have to assume standard early time physics and BBN constraint to get the omega baryon, and then the helium abundance, but still they get the same problem. And I would say one criticism that have been done to them is that to do that, they have to use BAO over a range of redshift, and therefore they have to use the BAO as seen in galaxies and the one as seen in the Lyman alpha. Some people don't trust the BAO as seen in the Lyman alpha, and I say no problem. You want to throw the Lyman alpha BAO out? That's fine, but then take the supernovae. The supernovae gives you a constraint on omega matter, even if you analyze them in a sort of model independent way. So which means H not independent way, not model independent way. And the answer won't change. And here again, this is from the latest EBOS data release 16 from the end of 2020, the same kind of plots. Again, that the problem is still there, even without invoking CMB data. So where is the problem? Is it in any specific data set? Well, it's not in CMB data, but all early universe-based determinations still hover well below 70 km per second per megaparsec. Many groups reanalyzed the shoes data and they found agreement with the published result. Several independent low redshift determination hover about 70. Now, not all of them. The tip of the red giant branch is around 70. But again, if you have 3 independent measurements, one of them is supposed to be outside 1 sigma, otherwise there will be an observer bias there. So as time goes on, it seems less and less likely that the problem is in any specific data set. A paper came out recently by Di Valentino et al., which is a review both of all the theoretical solutions that have been proposed and also of all the different ways to combine and select your data set to actually see if splitting the data one way or another, the tension disappears or not. And, it's 100+ pages paper. All the information is there. I just want to show you how thorough the analysis has been just by looking at, how many entries are there in terms of combination and comparison of different data sets. So what is the problem? If not in the data, then maybe in the model. And now this is, a loaded question. Galileo tried to do that and to deal and try to change what was the standard model by at that point, and the story didn't end up well. So we have to be careful when we do something like that. So if it's in the model, early time measurement assume standard lambda CDM at early time, and this is what gives the length of the standard ruler. Redshift zero measurement do not do assumption about cosmology. So shall we look pre-recombination or after recombination? Let's see. Maybe we can just change the length of the standard ruler as seen from the CMB. So let's look at the pre-recombination solution. So many people have tried to do that. However, this means that we modify the model right where we most like it. So it means that we have to change something that is either to do with the decoupling time, or to do with the sound speed in the early universe, or to do with the expansion rate of the universe at those early time, which expansion rate is given by the component of the universe at early time, which means we have to mess around with the components, which we don't like. We want to decrease the sound horizon by 7%, but without breaking havoc on the CMB, damping tail, and everything else. And this is a really tall order. Very smart people have tried, and they haven't managed to find a definite solution. They get halfway there, but not all the way there. And of course, halfway you go from 5 sigma to 3 point something sigma, but you still don't get all the way there. So a summary of this can be found in these two papers, Milea and Aylor, 2019. So what they basically conclude is that your wiggle room to actually do something and change the sound horizon to reduce it is in the decade of the expansion of the universe just before recombination. So this sounds to me a little bit fine-tuned. So if you do it before, you change nothing. If you do it afterwards, you mess up observation. So that's what you can do. And this is, it reminds me of fine-tuning, right? It's either extremely predictive and you know that you have to change things only there, or it's a little bit of a fine-tuning. So early dark energy affect the damping tail. So one can look for signature. You can play around with the initial condition, think about extra component, extra interaction, energy injections, change custom-made H of Z, change the inferred omega matter with scale, but these are not all equivalent. So the next generation of observation of the damping tail of the CMB, and especially the polarization, will be able to tell all the possible solution, palatable or not, apart. So what about post-recombination? So in post-recombination, solution include the screening, modification to GR, strange dark energy, and my take is that it's complicated because it would have to affect several different things at once, including time delay distances, which are a little bit more difficult to tinker with if you tinker with expansion history of the universe at early time. So you can try to increase the freedom of the expansion history of the universe, but the price is high because one of them many extra degrees of freedom, which reminds me of epicycle, or need to hide the change where there are not data yet. It's very hard to change RS by 7% if one has to tinker with omega baryon, which is hard. Omega matter H square means that you have to change that by 20% without changing other quantity that are well set by the CMB data. Sound horizon radiation drag, matter radiation equality, etc. And it's also hard to mess around with the standard ruler as seen in the BAO. So you could say, okay, maybe the standard ruler that the CMB sees is not the same standard ruler as we see in the baryon acoustic oscillation. After all, galaxies are biased tracer, or there could be some velocity bias or something like this. People have tried. You get 2-3%, but you don't get to 7%. These models are a little bit ugly. So you can re-ask yourself, well, so how much wiggle room in the middle is there? So what was done in this paper by my then grad student, Jose Luis Bernal, who has moved on to greener pasture, was to actually do a non-parametric reconstruction of the expansion history by looking at BAO data and supernovae data. And it turns out that even in a non-parametric reconstruction where this function history is described by splines, there's no much wiggle room to deviate from an expansion history that looks a lot like lambda CDM. So even if you give a lot of freedom to the expansion history, the data tells you whatever it is, it looks like a lambda CDM. I don't know the normalization doesn't match, but the shape is lambda CDM. So you can have wiggles up and down up to 5%, of course, because you have noise in the data. But here we really need, a different slope to bridge the two effects by 7%, which we don't see here. So I would argue in the last 5 minutes that if it is not a local problem having to do with the local measurement alone, then it's a problem well beyond H0. If we go beyond H0 or an RS NRD problem, then it becomes an omega matter problem too, and I would argue an age problem too. So the omega matter problem is shown in this plot. Again, always I assume an expansion history of the form of a lambda CDM, but baryon acoustic oscillation plus supernovae constrain an omega matter around 0.3. The cosmic microwave background constrain the sound horizon radiation drag, which is basically omega matter h square. CMB doesn't tell you omega matter, but it tells you omega matter h square very well. It's the physical density of matter, so it's here. And the shoes measurement gives h. And so again, you see another triangle here. This is a triangular conference. We're seeing triangles in all the plots. So there's a mismatch here too. If the late time observation of the universe, BIO and supernova, turn up with a low value of omega matter, then you say maybe it's an early versus late. But this is a late time measurement, and this is also a late time measurement. So there's something going on there.
5 minutes.
Yes, thank you. And how old is the universe anyway? Because if I plot the same quantity on a age versus age of the universe plot, then I also get something like this. This is the early time measurement of the age of the universe. Of course, the CMB can't measure the age of the universe because it happened before the universe became as old as it is. But within a model, yes, it yields the age of the universe so precisely that I have to blow up the error bars by more than 3 times for you to be able to actually see the Planck constraint in this plot. Otherwise, it would be a speckle and you wouldn't see it. So there's a mismatch here, and the question, which is big part of David Valchin PhD thesis, is there an independent measurement from the late time universe of the age of the universe? And here we go back to the 90s. The universe can't be younger than the oldest object it contains. And examples are old halo stars, or the classical example are globular clusters. Determine accurately the age of the globular cluster, for example, as his own skeletons in the closet, but it's a model independent determination. So it depends on stellar model, but not on cosmological model. So big part of his PhD thesis was to come out with a novel way to determine the age of the universe from the ages of the oldest globular clusters and from a very large sample of globular cluster collected from the literature. It's at the end, it's after selection is 22 objects, and that's where the late time universe tells you that the age of the universe should be. So lambda CDM seems to act as age, but not as shoe size here. So looking for Cinderella, can we twist the cosmological model so that we can also fit the shoes measurement? There's the bad, there's the ugly, but I'm not sure there is the good one yet. Maybe you can come up with a model like this. So here's an example of what the same plot would look for example, the early dark energy solution that only changed the early time universe. You see, the early dark energy solution helps a little bit in terms of H0, but it doesn't do much in terms of age. It doesn't get you all the way there. Before I conclude, this reminds me of the cosmic triangle. For those of us that were around in cosmology in the field in 1999, just when the evidence of the cosmological constant was coming along, there was this science paper by Bacall and collaborators that introduced the cosmological constant by introducing the cosmic triangle. You have three quantity, omega matter, omega lambda, and omega k. They need to sum up to 1. And so this triad type of plot was very useful to actually bring all this evidence together. Now, 22 years later, we go back to the future. And I suggest that now we have actually 3 over-constrained systems, which they don't sum up, but they multiply up to a constant. One is omega matter h square, omega matter and h square. The other one is sound horizon radiation drag h and the combination of sound horizon radiation drag times h. And the other one is h naught, omega matter and age of the universe. And so these are over-constrained systems because you measure 3 quantities which you believe are independent, but actually they are not. So it's an over-constrained system. So using this kind of plot is very useful to try to see what kind of model will actually put all these constraints to cross and agree with each other rather than being different parts of the plot. So let me come to the conclusion. I don't have a theoretical solution, but whatever theoretical solution that we come up with should not break havoc where havoc is not needed, should preserve the good agreement of lambda CDM with the data, and should improve and not worsen other tensions. We should quantify improvement versus predictability. There are some parallelism with lambda. And we should always bear in mind whether the measurement is model dependent or model independent, and ask at what point we are adding epicycles. The Cassini model had epicycles. The Copernican model also had epicycle, but the epicycle in the Copernican model were epicycles that were putting us in the right track because the orbits were still circular, while we know the orbits are elliptical, and the epicycle were correcting for that. But these were epicycles that were putting us in the right track. So I hope that I sort of propose a way to actually see the observational constraints as guardrails that will tell you where to put epicycles so that it will offer some direction to actually look for a solution, even though we don't have the actual solution in hand. And I presented one of those possible tools to do that, which is this new cosmic triangles. And I'll stop here. Thank you.
Thank you very much, Licia. There's a number of questions already. I think Joe Silk first.
Hello there. I'm not sure if you can see. Can you hear me?
Yes.
Thank you, Lydia. That was great. I really enjoyed the overview. I do have one question, which I'd be curious to get your comment on. It seems to me that if we're really going for new physics, we need a really, really strong case. So what worries me somewhat about throwing systematics away as an explanation is that we have a wonderful theory of the cosmic microwave background. We have a pretty good theory on the tip of the red giant branch. And so in between those two probes of H0, they are giving a discordant value from the Schu's value. And the problem then may be that we don't really have a decent theory of supernova explosions and on all sorts of possible issues connected to that. So I just, I think there is an issue here that one has to be very, very careful about. I wonder what your comments are on that.
Yeah. Actually, for speed, I skipped this slide where, let me see, where if I was saying that if the age of the universe is confirmed, model with IH0 and standard low redshift physics, we have to be careful, right? So there are two possible scenarios, local and global. In the local, you affect the H0 measurement and leave all the rest unchanged. So which means that maybe we learn about Cepheids. Maybe we learn about how to calibrate Cepheid to supernova. The tip of the red giant branch also relies on supernova. So we can't tinker around with supernova, but we can tinker around with Cepheids. Or then you need a global solution. But yes, indeed, we should not throw the systematics completely out of the equation, but they're likely not silly systematics or mistake systematics. They're probably going to be systematic that will tell us something interesting anyway. Maybe not about cosmology, but definitely about something.
Yes, thank you.
Okay, next question by Dimitri Semikos.
Yeah. Oh, thank you for a very nice talk. My question is related to somewhere 1 year ago, there was a solution by Jdamzik and Pogosyan to adjust primordial magnetic field to lambda CDM, which anyway is there, just always assumed to be 0. And then it's just mild extension to practically solved. So could you comment, do you think the status of this solution is not the same, or?
So if you remind me what the solution was. So if there are primordial magnetic field,
then there is no problem with the Hubble tension. You just correct lambda CDM model with adding primordial magnetic field, and then it's Hubble would be consistent with observed today.
So this primordial magnetic field will change the inferred sound horizon radiation drag from the cosmic microwave background to bring it down.
Yeah.
Do?
Yeah, I think it would just change it's to.
Because yeah, if they change the inferred sound horizon from the CMB, it's still. So it should be compensated by omega mater, and the low redshift universe tells you that omega mater is still 0.3. So we have to make sure that whatever that solution does, it doesn't mess the agreement between temperature and polarization, which probably they've checked, but also that it doesn't push the other parameters around to still give a good fit to the cosmic microwave background, and then get an omega mater that is different than the low redshift omega mater. And I don't know that. I haven't gone in detail through that. So that's the risk of just changing our, the sound horizon radiation drag. But we can look into that.
Okay, I don't. Okay, let's see. Thanks.
Okay, next question is by Shaheen Shaikh-Jabari.
Thank you very much for your very interesting overview talk. Actually, I wanted to point out to our new paper, which I just put its link here. And the proposal we are making is perhaps the FRW framework may not contain the answer to the Hubble issue that you just reviewed very well. And what do you think about looking out of the FRW box? So that there are, as we argued, there is no way to basically within the FLRW cosmology to get any H0 above 71, no matter how we play with early or late dark energy. So
okay,
I'd like to have your comments on this.
Okay, so if you throw away FRW, I understand correctly that then so FRW, it's homogeneous and isotropic.
Yes.
Right.
Yes.
So you're throwing away the cosmological principle.
Exactly. Yeah.
So we're throwing away lambda CDM, not at the level of actually, adding an extra component or, changing the interaction between two components. We are changing it down to a much more basic level, which is like we're changing the metric completely.
Yes.
So,
yes,
and
yes.
would that be still a GR solution, or you have to?
Sure. Why not? Why not? Of course. Actually, we argued that within FLRW cosmology, no matter how you play with the dark energy sector, early or late, it doesn't fetch you H0, which is above 71 plus minus 1.
Exactly.
That's
you halfway there, but not the whole way. Yes, exactly.
So you can never reach anything close to 73, 74.
Yeah.
And in particular, if we add the constraints from the age of universe that you mentioned. So that's one part. And then there are other observations or analysis on the quasar data around redshift 1 or above, that actually tells us that we are not in the Hubble flow even at that redshift. So there is a sort of cosmic dipole, as if we have a cosmic dipole. So there are some observational evidence for this.
So you say instead of throwing away the lambda CDM, but keeping the pillar on which the lambda CDM is built and tweaking around with the lambda CDM, you're saying, let me throw even one of the lambda CDM pillars away, which is the cosmological principle.
Yes, because if you keep that, the framework does not allow you to get close to risk measurement.
Right.
And we have actually arguments for this, and there are evidence from the data at different redshifts that maybe isotropy should be revised. Actually,
it's interesting, but it's scary.
Sure, of course. But
okay,
we have tried many different solutions, whatever we could, and we couldn't basically resolve the tension, as you reviewed, right?
Yeah, as Sherlock Holmes said, once you rule out
yeah,
the obvious solution, then you go for the not obvious one.
So this is exactly the quote that we have in the abstract of our recent paper. Exactly. Thank you. Thank you.
Thank you. One last question, George Smoot.
George, you are muted. Now, no?
Yes, okay, if I hold it down, it'll unmute. All right, Licia, thank you very much for your talk. I was trying to have a conversation in the chat, but I was unable to put the figure in that was important for what I wanted to do. For some reason, it wouldn't let me load it. I had argued very hard a couple of decades ago not to people for use the term the Hubble constant. And you, of course, in your plots only use the Hubble. I lost that. Adam Rees pointed it out to me twice because I brought it up with him twice. You use the Hubble constant, which means you're extrapolating everything down to the present time. And that means you mix the theory with the data, with the observations, and you therefore have to give these arguments about changing this factor does this and that kind of stuff. Whereas if I can figure out how to share my screen, let me see if I can do that, if I'm allowed to it. Of course, I'm not. It must be that
allowed.
I didn't start my video or something. All right, you see me being lazy here. Okay, now let me try again to share the screen. Come on, I'm the wrong desktop. How do I get back to the desktop? So what I was gonna do is show you.
George, you're muted again.
Oh, sorry. If I could figure out how to show you this plot, let me try.
Is the plot somewhere online? You can just send us the link.
Yeah, I can do that. But if you just look at the Hubble expansion rate versus time versus the observations, you will find a smooth curve that goes down to a minimum now redshift 1 and then comes up sharply. But way above that, requiring a tremendous turn up, is the the shoes data. And what you realize is you've got to tweak. It's easy to get the data to go through the model to go through the other observations, but it's very difficult to get it to go through the shoes data point without having something terrible wrenching going on in the present time. And somehow, let's see if I can share, but I can't figure out how to.
So you can't stretch this ladder too much and you can't twist it. It's just that it doesn't quite land correctly on both sides.
George, you're muted again, but I think we'll have to move on to the next talk. All right. Let's thank Licia again for a very nice talk.
Thank you.
And then let's move on to the second talk of the session by